Here we are, simplifying trig expressions. So it's important to listen to the thought process behind the steps. So the steps are one thing, but if you just look at the steps, they're going to kind of seem like they came out of thin air, and you're going to be like, why is he doing that? And it's different for every problem. There's some similarities, but if you start thinking about the thought process, eventually you'll get these no problem. So for the first one, I'm supposed to simplify here. I've got sine squared of x times the cosine squared of x plus cosine to the fourth of x. So I'm looking at this and I'm seeing sine squareds and cosine squareds, even cosine to the fourth. I'm thinking down the road I might end up using some of those Pythagorean identities that we worked with earlier. Oh, a quick note in case you've forgotten. This idea of sine squared of x, it just means to take sine of x times itself. Okay? Now, sometimes we'll use that, and sometimes we won't. So, the next thing I notice as I think about simplifying this trig expression is I notice that there's some cosines here, and there's also some cosines here. We've actually already done this problem in the factoring review section. It was organized a little bit different there. There it looked like this: x squared times y squared plus y to the fourth. But you notice it's really the same structure that we have here. Sine squared times cosine squared plus cosine to the fourth. Over here we just factored out a y squared from each term and got this. We're going to do the same thing here. We're going to factor out cosine squared of x from each term. So if I take this and I divide out a cosine squared x, and I take this and divide cosine squared of x, you'll notice over here these terms cancel. I'm left with sine squared of x. Over here I have 4 cosine x's multiplied together on the top and 2 on the bottom. So I can cancel out 2 from the top and bottom, or divide out, and I'm left with cosine squared on top. And this is very good. It's early on, you might not realize why this is very good. But if we go back to the Pythagorean identity, you see here, whenever we have cosine squared of an angle plus sine squared of an angle, it's always going to equal 1, no matter what the angle is. So, we can now use our Pythagorean identity, sine squared theta plus cosine squared theta equals 1, and we can replace it with 1. So, this first expression is equal to that. This line is equal to cosine squared of x times 1, which is just equal to cosine squared of x. Quick side note, be a little careful with your 2's and your squareds. This almost looks like cosine of 2x. We want to make sure it's smaller and high enough that it looks like cosine squared of x. Alright, on to the second one. So one strategy that we're going to use is factoring. We're also going to use Pythagorean identity. If you look at this next question here, you notice it's pretty different than this first one. This first one, a lot going on, sine squareds, cosine squareds. Here, first of all, we don't have any sines or cosines, but we don't have any squared terms either. We just have cotangent theta over cosecant theta. So when I'm looking at this, I'm thinking, oh boy, what should I do? Maybe if I change these all to sine and cosine, maybe something will cancel out. Maybe this will be helpful. Well, think back to earlier. What is cotangent theta in terms of sine and cosine? Well, hopefully you'll remember cotangent theta is cosine theta over sine theta. And cosecant? Well, hopefully you'll remember that cosecant theta is the reciprocal of which function? Hopefully you said sine. And vice versa. I can write sine as the reciprocal of cosecant. Alright, back to the problem. To make this a little easier, I'm actually going to break this fraction up and kind of treat them separately. You could do one giant fraction, and maybe I'll do that in a second. But I think you'll see this method is a little bit easier. If you don't see it at first, that's fine. Alright, so all I've done is split the fraction up. I've taken cotangent theta times 1 over cosecant theta. If I multiply this, I would just get back to here. So, replace cotangent theta with what it's equal to. Cosine theta over sine theta. And 1 over cosecant, well, you see over here, it's equal to sine. So I can just replace that with sine of theta. Just a couple of substitutions, that's all I've done. Hopefully you're liking this. Hopefully you're noticing something that's really useful here, is that the sine thetas cancel out, and my final answer is cosine theta. Now, maybe you didn't like some of the fraction tricks that I did along the way, and you're not seeing that. So let's call this method 1, and let's try a second method. Alright, so let's say for this, you're looking at it, and you're like, okay, cotangent theta over cosecant theta. Alright, I see some relationships, I see some substitutions, but I don't like this fraction stuff. Fine, go for it. Just replace cotangent with cosine theta over sine theta. Now, divide cosecant. Well, cosecant we know is 1 over sine theta. Yeah, not sure if that's easier or not. You could think of this as just a problem where we multiply by the reciprocal. Instead of taking cosine theta over sine theta, think of that as a division. Divide by 1 over sine theta. But now instead of dividing, we want to multiply by the reciprocal. So I get cosine theta over sine theta times sine theta. These cancel, and I get cosine theta. Now here's the deal. At this point, you're probably thinking, I think I like method 1 better. But you might not see method 1. You might have no idea what to do with this problem when you first look at it. And so, something that is relatively simple and easy to do is start doing some substitutions. If the substitutions lead you to a simplification, something that's easier than what you started with, great. If not, back up, try again.